We are privileged to have with us today a distinguished personality in the field of engineering materials, Professor Dr. R.Jayaganthan from the Department of Engineering Design, IIT Madras. He is a pioneer in the area of engineering materials in India. He has successfully guided 31 PhDs and more than 100 MTech students in the various areas of materials engineering. He has published uh, 315 journal articles in peer-reviewed international journals. He has made a significant contribution for the development of ultra-fine and bulk nanostructured materials and additively manufacturing aluminum alloys for structural application, covering material processing, mechanical behavior, and corrosive properties. He has established manufacturability of aluminum alloys using both SPD and additive manufacturing for production of lightweight structured parts in an automotive and aerospace application. His an innovative applied research works lead to several patents in the domain of material design and kinematics and dynamics of machineries. He is a fellow of International Academy of Engineering and fellow of Institution of Engineering, India. We are indeed honored to have such a renowned expert with us today. We are looking forward to an insightful and engaging session, sir. Once again, we extend a warm welcome to Dr. Jagannathan, sir, and to all the participants.
Yeah. Thank you, Dr. Vinod. I hope I'm audible to you.
Yes, sir.
Yeah. Very good evening to all the participants who is attending this faculty development program. Before I start at the outset, I would like to thank Dr. Vinod Kumar for giving me this opportunity to deliver my talk in this particular faculty development program on emerging trends in advanced material. So I'm just going to share my screen. Give me a minute. So, Dr. Vinod, it is not allowing to share my screen.
Sir,
It is not allowing to share my screen.
one
You
minute,
have
sir.
to do from your
One
end.
minute, sir. I
Yeah,
am enabling to you, sir.
yeah,
Sir, now I enabled to you, sir.
yeah. I'm just trying. No, again, maybe I will.
Sir, now you can share your screen, sir.
Again, I'm not able to share the screen. It says you are not allowed to share the screen. Dr. Vinod,
So, 1 minute, sir. I am checking.
take your time now. Cool. Take your time, and I will wait.
Sir, it's enabled only, sir.
No, I'm not able to. Maybe I will.
1 minute, sir. 1 minute, sir. My screen is presenting here. That's why, sir. Now you can present your screen, sir.
Again, same problem. You are not allowed to share your screen. You can ask the meeting host to turn on screen sharing. Or if it is not working, I can send my PPT to you. You can try to display the PPT from your end.
Okay, sir.
You please check. Yeah. Yeah. Now I'm able to. Yeah. Please.
Yes,
Just wait a
sir.
minute. Yeah. So this screen is visible.
Yes, sir. Now your screen is visible to us, sir.
Yeah. So hope I'm audible to all of the
Ye-
participants, and in fact,
Yes,
they
sir.
can also
You are.
interact during the course of my presentation. If anybody wants to interrupt, also absolutely fine. I assume that once again, a very good evening to all of you. In case if I'm not audible, Dr. Vinod, you can send me WhatsApp message. I don't know whether No, I am being continuously audible to all the participants or not. In case if you find it I am not audible to you, you can immediately send me WhatsApp message. Is it okay, Dr. Vinod? Hello.
Sir?
Am I audible? I want to
Yes,
ensure
sir.
I am
You are
audible.
audible, sir.
In case if I am not audible, I request you to call me or send me WhatsApp message.
Sure, sir.
Yeah. So once again, a very good evening to all of you. Today I'm going to give my no, lecture on fatigue behavior of additively manufactured aluminum 2024 alloy for aerospace applications. In fact, no, I'm professor from the Department of Engineering Design, and Dr. Vinod has already introduced about me. So you are all aware. I assume that most of you are with mechanical background. You have studied a manufacturing course, kinematics and dynamics of machineries, design of machine elements, a lot of fabrication techniques, for example, welding, no, welding technology, and so on. So why additive manufacturing? In fact, yesterday itself it has started this faculty development program. In fact, you might have already attended additive manufacturing related topics, also basics. So before I discuss in detail today, the development of aluminum alloys. In fact, aluminum alloys they are used extensively in aerospace application due to its very high specific strength. Strength to weight ratio is always desirable for all automotive application, aerospace applications. We always look for lightweighting. Strength to weight ratio should be very high. Right now, aluminum alloys, we are already using it in aerospace applications. Different parts of the aircraft, we are using extensively aluminum alloys. Of course, high-end aircraft, we are using extensively polymer-based composites also. Basically, looking for very high lightweight. In fact, the specific strength to weight ratio is much higher for polymer-based composites. You already done course on related to manufacturing. Why additive? You know the definition of additive. We always say that layer by layer deposition of material. The process you end up in getting the final shape of the component what you want to produce. Rather, I call additive manufacturing as bottom-up approach. In the conventional manufacturing, all of you are aware how do we get the final component. Right from the beginning, you have to extract the metal or alloys from their corresponding ore or mineral. The molten metal or alloys, they need to undergo solidification through casting route. You are all aware about casting, foundry technology. Through casting, you end up in getting different shape of the let us say your solidified casting may in the form of billet, bloom, or slab. You produce variety of shapes going through solidification route. You are producing casting. Casting could be of different shape. I mentioned about billet, bloom, slab, and so on. These billet, bloom, and slab, and so on. Basically, they are subjected to further processing. Rather, what I want to highlight before I go in depth into additive manufacturing, having mentioned or defined additive manufacturing is nothing but bottom-up approach, wherein we deposit the material in the form of layer by layer. In the process, we are also going to discuss what does it mean by layer by layer deposition, how we are making use of laser as energy source to ensure that layer by layer of deposition of material, we end up in getting the final shape of the component. The conventional manufacturing is called top-down approach. What do you mean by top-down approach? I produce the casting. Casting, it needs to be subjected to variety of thermomechanical processing techniques. You are all aware about forging, open day forging, closed day forging, likewise extrusion also. You know about extrusion. There also we have open day, closed day extrusion, and then rolling. If you want to produce it, we use rolling technique. And if you want to produce wire, we use wire drawing. That means from starting with the bulk shape of the casting, you are subjecting it to variety of thermomechanical operations such as forging, rolling, extrusion. Finally, depending upon the component you want to produce, we make use of variety of machining techniques, end up in getting final shape of the component. That means what? Subtractive manufacturing is nothing but conventional manufacturing, top-down approach. You start with the big shape, end up in getting final shape of the component. But in additive, directly we get the final shape of the component. Your starting material in this case, we are using either powder or it could be wire also. Starting material to do 3D printing of any component, we begin with either powder Basically, I'm confined my discussion to metallic material. Okay, I'm not going to discuss any chemical-based technique like to do any 3D printing of any objects. I'm confining myself to metallic material, for which when you go through 3D printing, we begin with either a powder or a wire. So I want to define additive manufacturing is nothing but layer by layer deposition of material in the form of powder, and each thin layer of powder, when you just put it on the build platform, we scan it with the laser. Like in conventional casting also, like here in additive, your material being sprayed in the form of powder, when you scan it with the laser, it undergoes instantaneous melting followed by solidification. Here also it involves like liquid to solid transformation, rather it involves solidification process also. Since we are beginning with a very thin layer of powder, it is possible to play with the cooling rate. Rather, when you use laser source for thin layer of powder, I can ensure the whole thin layer of the powder, when the laser is striking upon that, it undergoes instantaneous melting. Basically, I can have very good control over the sort of solidification. Rather, we call solidification kinetics. I end up in getting very good microstructure. Rather, it's called a well-refined microstructure. Likewise, each thin layer being micron thickness, when you shine it with a laser will enable to ensure the uniform melting of the whole powder layer. As a result, we'll end up in getting the well-refined microstructure. That means by depositing layer by layer, one above the other, by scanning it with the laser, the final shape of the component, internally, if you look at through microscope, you'll have well-refined microstructure. Unlike in casting, in additively manufactured material component will have well-refined microstructure. If you recollect your manufacturing course in casting, okay, we produce very big casting. Surface will have different microstructure compared to the interior. We need to account for uniform cooling of the whole molded metal undergoing solidification. Surface may undergo very fast cooling compared to the interior. That's where core structure highly segregated dendritic structure compared to the surface. Again, I'm referring to what I mean by microstructure for material. Any material, if you look through naked eye, it looks continuum. But when you see through microscope, depending upon the length scale you are looking for, it may be millimeter length scale or micron length scale. Rather, I call it as heterogeneous microstructure. Internally, you end up in seeing different grains or crystal, which makes up the whole material. I'm referring to additively manufactured material. The internal microstructure, if you see through microscope, is highly homogeneous microstructure, rather well refined. Whether you look at the surface or core, we end up in seeing the homogeneous microstructure. Ultimately, why I'm highlighting microstructure should be homogeneous or heterogeneous? Ultimately, properties dictated by internal microstructure. Again, when I say microstructure, the internal physical features of the grain or crystal, how they appear, what is their size and shape. From design perspective, I want to know the geometrical architecture of the grain or crystal, how they appear. Is it sphere-like structure? Whether we use different terms for referring to the grains or crystal in the material. We call columnar structure. Okay, columnar is pillar-like structure. Dendrite is like needle-like structure. Laminar structure is like plate-like structure. We use different terminology to characterize the geometrical shape of the grains or crystal in the material. As long as it happens to be the uniform grains having same dimension in all direction, that we call equioxide structure. What I mean by equioxide structure? Having same dimension in all direction, well refined grain, having same size and shape in all direction, that I refer it as equioxide structure. Through 3D printing, since you are starting with layer by layer of powder, it is possible to have very good control over the solidification. Ultimately, manufacturing, you are aware, liquid to solid transformation. In additive, you are able to have precise control over the cooling rate of the material which undergoes melting followed by solidification. As a result, by playing with the process condition appropriately, you end up in getting the well-refined microstructure in 3D printing unless in conventional manufacturing. Conventional manufacturing, if you want to produce any component, we have to go through a series of steps. At the end, you see, it has to go through a variety of machining operation, lot of material removal. Through conventional manufacturing, it is going to take a lot of time and cost also, not cost, a lot of time and a lot of materials loss actually. I mean. So in order to overcome that, we go for additive route. So what I just highlighted right now, we are just differentiating additive from conventional. Conventional manufacturing is called subtractive. You begin with a big object and then we are reducing the dimension ultimately to end up in getting required size and shape of the component. We call subtractive. Subtractive manufacturing involves variety of steps, variety of techniques. There is going to be a lot of material wastage, lot of time is involved, and any intricate shape and dimension if you want to produce that is going to be very tedious in the conventional manufacturing. Additive, I mentioned about bottom up approach. We are also going to discuss how the process it takes place when you do 3D printing. In 3D printing, normally we try to give CAD file from computer that is basically STL file. And STL file, when you give it to printer, printer basically then it understand what kind of shape and size and shape of the component needs to be produced. So printer basically, you're all aware about kinematics. What kind of movement is required for the printer? It understand depending upon the STL file what you give. So laser also accordingly it will try to do scanning over the thin layer of powder. I'm also going to show the figure also. So hope it's clear right now. I'm just defining what I mean by additive and how is it different from conventional manufacturing. And advantages also you can see, any complex shape can be produced. Weight saving is going to be much more greener compared to the conventional manufacturing technique. And of course, we in terms of environment also, you say it is not going to be harmful to the environment. And portability, wherever you want to produce the component, we can take the machine there itself, and it's possible to produce the kind of component what you want to produce. Of course, the disadvantage we say that the initial cost is going to be high, but again, it can offset. For example, if you take aero engine component, looking at the material cost, if you go through the conventional manufacturing, we cannot generalize. In some cases, cost may be prohibitive, but it's not for all the cases. For example, aero engine component, we can say additive is better than compared to using conventional manufacturing. And of course, additive, no, when we say limited material, we cannot print just like that any material. First of all, the powder or wire, what you use it for 3D printing needs to be qualified. Is the powder qualifies to do 3D printing? That means powder characteristics in terms of size, shape, the purity, everything needs to be ensured actually. Their flowability. Powder has to be qualified before taking it forward for doing 3D printing. And again, unlike in conventional manufacturing, we have casting, going through a variety of stages, and we need to do a lot of other post processing. Added to the number of post process steps involved, relatively are very, very less compared to the conventional manufacturing technique. And again, if you look at this slide, I hope I'm audible, Dr. Vinod. In between, I'll be asking whether I'm audible or not.
Yes, sir, you're audible, sir.
Yeah, yeah. Please look at this particular slide, left side. We try to compare no, additively manufactured component with traditionally manufactured component. So the additive is suitable for low volume production. For example, taking a patient specific implant, high performance aerospace component referring to engine component. So obviously for low volume production, you can always prefer additive. Like this extreme right side, if you look at, obviously, if the component shape and size and shape of the final component is very complex, okay, obviously better to go for using additive rather than going through conventional. Reason being, the intricate shape, if you want to produce, it might involve a lot of material removal. You may not end up in getting the exact dimension what you look for actually. That's where that beauty of going through additive route. And the additive route to begin with, we are giving appropriate CAD file, and we can do a priori not topology optimization for the component what you want to produce through software actually. That's where you can look at the bottommost. We can produce a person-specific implant, and also giving the example in the satellite rocket NASA also a lot of internal cooling channel. Basically, we can direct it to 3D printing. And again, when it comes to cooling channel, we talk about heat exchanger. The heat exchanger, the internal, the size of the feature component, they always lie in the range of micron, submicron size. These micron, submicron level features of any heat exchanger that can be produced easily by 3D printing compared to conventional. Conventional is going to be very tedious actually. You may not be able to maintain the exact size and shape of the submicron feature size of the component. That's where it's better to go for using 3D printing. Just giving few example. In fact, the esteem right you see bracket. Bracket could be like stating it may be taking either static load or dynamic load and so on. This topologically optimized bracket, it can be directly 3D printable. We are just saying that For low volume production, go for additive. And the highly complex shaped part, if you want to produce, better to go for additive. Reason being, in the conventional manufacturing, it involves a lot of material removal, and you may not end up in getting the required size and shape of the final component. Actually, that is there. We are just comparing conventional manufacturing with additive. Hope my slide is moving. Yeah. And again, you are all aware about the variety of the 3D printing technique. And see, each technique is unique. What I want to highlight, you cannot produce any size and shape of the component by just using one 3D printer. And what you see is extreme right, selective laser melting or electron beam melting. Second one, direct energy deposition, laser powder. Third one, again you see we are using wire-based DED. And extreme right, you see we have electron beam additive manufacturing. Along with we have wire direct energy deposition. What is that you see from extreme left to extreme right? Any component with a complex geometry, if you want to produce, what is their internal features architecture in terms of looking at the internal feature, their size falls in micron or submicron. As I mentioned about heat exchanger, the internal feature size could vary from micron to submicron. And some parts, like the massive part, your feature size may go even millimeter also. That means what? One single machine, the way it has been designed, you cannot use it for 3D printing any kind of material, end up in getting different size and shape of the component. If you want to produce the intricate shape of the component, wherein internal size features are only micron, submicron, you need to maintain very, very low deposition rate. That's where extreme left you have to choose selective laser melting or electron beam melting. The way the machine has been designed, it only ensures very, very low deposition rate. Only through very low deposition rate, you are able to maintain the smallest size features, micron to submicron. If the future size, if it is of the order of millimeter, we can always go for machine which can ensure very high deposition rate. It is like saying it is not one printer can be used for printing any size and shape of the component. That's where there are three different variants of 3D printers. Principles are same. We are using either thin layer of powder or wire. We are scanning it with a laser. It undergoes controlled solidification. But again, the way you use the process variable, that is going to dictate the kind of dimension or size and shape of the component what you are going to achieve. That's why I'm trying to highlight from extreme left to extreme right. We have wire-based data energy deposition, powder-based data energy deposition also. You can see laser powder DED 2.27 kg per hour. And if you look at the extreme left, 0.1 to zero point 0.2 kg per hour. For example, if you want to do weld repair, which one you will use? If I ask you, having listened to my input, if I ask you, you want to do weld repair, if a lot of components in aerostructure also, they don't want to just dump it immediately. Non-critical parts, they want to repair it actually. For through fabrication process like welding, we will do a lot of operation. We'll do welding operation to fabricate. You want to repair the weld or you want to join broken parts, you want to connect it. As long as it happens to be non-critical part, the broken parts you want to join. You know about the role of welding actually. For weld repair, which one you will use? In fact, they propose wire arc based additive is helpful for weld repair. Which one you'll use? Let us say heat exchanger, the typical size and shape is micron or submicron. We always go for using circular laser melting where deposition rate is very, very less. I cannot use for weld repair using the circular laser melting or electron beam melting. The deposition rate is very less. That is utilized only for making very, very complicated size and shape of, for example, in the previous slide I showed about the topology optimized bracket actually. Very complex shaped geometry. Looking at the internal size feature, if it is few micron or submicron thick, you should always go for extreme left actually. For weld repair, obviously you can go for choosing the single wire DED 2.9 kg per hour deposition rate, or you can see the extreme right electron beam additive manufacturing. There also we have wire based direct energy deposition. You can see 11.34 kg per hour. There you cannot get a very minute features like micron or submicron. That's where we go for using extreme right actually. I'm just saying with respect to use case or application, you have to pick up appropriate additive manufacturing technique wherein we make use of laser or electron beam melting. I'm trying to highlight metal based 3D printing. What are the available techniques? We have a lot of 3D printing machines in India. If you do proper auditing, more than 50% of the machine they are ideal. Lot of private players, they buy the machine. They only want academic institution to go and do printing and pay money to them. Some company, they come forward to collaborate. They try to develop some prototype jointly. Whereas most of them, they just buy machine. It is not being effectively used. Simply, it is imported from abroad. For information, now 3D printing is machine is made indigenously in India. There is one company, Intech in Bangalore. They produced low cost 3D printing. Possible to get 3D printer with the cost of just 70 lakhs. It used to cost 3 crore, 4 crore. Now the price has come down. Okay, we are equally capable to produce indigenous machine, electron beam melting as well as even self laser melting. Once again, for information, the laser source is critical for no, developing 3D printer. Laser source also in indoor, if you are aware about CAD, is one of the Department of Atomic Energy unit. Is called CAD. There they are producing laser source also. If some of you are entrepreneuring, if you are focusing towards startup, tremendous scope within India itself, you can develop your own 3D printer. Even for lab scale 3D printer in your college, you can make it. If you are able to get funding, you can design and develop your own 3D printer for metal, and polymer is quite easy actually. For polymer, depending upon features you're looking for, machine could cost varying from 1 lakh to even 40 lakh, 50 lakhs, and so on. Metal based printer also is cheaper. I'm saying it's possible to procure, purchase laser source within India. One can design and develop this 3D printer. It's basically what vacuum chamber and use laser source and you connect it to embedded hardware and so on. You can usually make our own machines. Otherwise, in the last 10 years, if you see all the machines we import from abroad, okay. So obviously, our all resources are getting, exhausted. We buy oil from abroad, all high-end equipment buy from abroad. Virtually nothing. We don't make many expensive component machines locally. Now the trend is changing. The startup culture in India, trend is changing. I mentioned about 3D printing machine. It's being made indigenously within India itself. I'm just trying to highlight. I don't want you just like seminar on this particular topic. You should also know this machine, is it purchased? Is it possible to purchase within India? To answer this, we can purchase machine locally. It's also possible to develop this machine locally with your expertise in mechanical by interacting with your people in electrical and electronics. Possible to make your own machine. Reason being, any design can be reverse engineered. In the process, you can always revisit the existing design. You can come out with your own design. Possible to make everything virtually before going for making the real machine. What I mean by virtual machine, 3D printer, you know what specification you require. Everything through CAD software, you create each subsystem, you create a CAD model. You can do optimization. Okay, everything can be done virtually by using simulation. You're all aware about FEM simulation. You know about CAD software. Virtually, you can create everything. Even the whole process dynamics can be simulated. What is going to be the final property, that also can be simulated. We can relate from the processing to the microstructure. Microstructure in turn can be related to properties. Whole stuff can be done in computer. We can do simulation. We can optimize it. That means what? You don't need to spend a lot of time. There is nothing like trial and error way of making common. Everything has been accounted through simulation with your domain knowledge by making use of appropriate software. Possible to make the virtual machine before going for making the real machine. That is possible. All the information is available with the availability of AI tool. You have the complete database of design, process related stuff, material related stuff. You call this database. You can link your AI database with your FEM software with your domain expertise. Possible to make your own machine. If you ask me what expertise required to make a machine, you have to be good at kinematics and dynamics and machineries, wherein you are all aware about different mechanisms, planar mechanism, spatial mechanism. That will account for how the printer head should move. Because we are laying thin layer of powder, we are scanning with the laser. Basically, you need to get into kinematics, dynamics, and machineries. And ultimately, the printed part, additive part, you have to see what process conditions are involved, how can control over that. So it's all basically accounting for your kinematics and dynamics and machineries, thermodynamics, heat transfer, fluid mechanics. All these concepts need to be used to do simulation computer. At the end, you will be able to make the actual machine. So once your design details are clear, having done simulation, you can take these details to make manufacturer can assemble each individual part. As I mentioned, you can buy laser source from indoor. Individual spare parts you can buy. You can assemble them. It's possible to make 3D printing machine. Yeah. And again, if you look at this, as I mentioned, the extreme left, what you have. No? Basically, we have vacuum chamber wherein we can make use of the inert gas like nitrogen or argon gas. Extreme left, what you see, basically the build platform, you just put thin layer of powder and we use rehoter plate to ensure that we are having uniform thin layer of this powder. And when it comes to the extreme right, you can see the roll of laser beam. So it does scanning actually. So scanning also there's several pattern. It can be zigzag pattern, meander pattern, the way it has to scan. Again, that depends upon what kind of typical dimension you require for the particular final component what you want to make actually. So laying thin layer of powder, scanning it with a laser, it is being done repeatedly layer by layer. So layer undergoes melting, solidification instantaneously, it forms thin solid, and again second layer powder is being laid over the platform. Again, laser is being scanned. This process is continued. End up in getting three-dimensional shape of the final component what you want to produce. And again, before you go for making the actual component, what they try to do first they need to establish properties for the material. For that, they try to print test coupon. What do I mean by test coupon? First of all, you have to ensure material being printed through 3D, no, printing like a different laser-based technique. Material property needs to be ensured. I cannot go for straight away printing the final shape of the prototype actually. Hope you're getting. My seminar is also basically to characterize 3D printed material, where it is capable of providing desired mechanical properties similar to the conventionally casted material. You can say that it may be wrought alloy or cast alloy. First, you need to qualify material property. Material is being produced through 3D printing. We call test coupon. And once you ensure the test coupon material printed, it provides record static and dynamic properties. When I say static properties, I'm talking about tensile strength, compression strength, and fracture toughness. When I say dynamic properties, I'm talking about fatigue strength, and a cyclic load, how the material is going to behave. Once you establish properties of the material, which is 3D printed, then I can take the material property as an input to design the prototype. What is after prototype? Prototype is nothing but you've taken the material with the record property that it has taken a particular shape and size that I call prototype. It has to deliver certain functionality. Obviously, you should know what makes up that prototype. We need to choose selection of material. Any prototype to be made, as a designer, I have to pick up the material. How that material was produced. Is it by casting route or 3D printing route? What is the property going to be? As a designer, if you are involved in procuring material, before you process them, shape them to achieve final shape of the component, I need to see what is the technical specification of the material what you procure. When I say technical specification of the material, in this case 3D printed, can it fulfill the record or desired mechanical strength, tensile strength, ultimate tensile strength, fracture toughness, whether it provides adequate ductility. Obviously, for no, high strength application, not only ensuring very high tensile strength, and it should be able to provide very good ductility also. Any application, you should ensure good combination of strength and ductility also. So ductility takes care of if at all sample is deforming, it is able to take plastic strain. They should not break into pieces immediately. It should not be brittle. I'm using the term called ductility and brittleness actually. Brittle material, it will not take any plastic strain at all. For example, ceramic plate, if you drop it over the floor, obviously it will break actually. Aluminum can, if you drop it from the height, obviously they may bend and deform. Aluminum can, if you drop it over the floor, it may change its shape. It means that it is not going to break into pieces because ductility takes care. It has very good strength and ductility takes care. If at all they fall, for example, aluminum can, dude is very good ductility. It's only changing its size and shape. That's all. I mean. So I'm just trying to highlight what happens in laser powder bud fusion. We are using thin layer of powder, scanning it with the laser. It undergoes instantaneous melting and solidification. As a result, going through the process layer by layer, we end up in getting final shape of the component. As I mentioned, if you want to build a new prototype, first I have to establish material what you want to print, and we have to qualify the powder first. Having qualified the powder first, you do 3D printing of the material, test coupon. The test coupon data needs to be generated by doing a testing, static test and dynamic test. Static test, you are aware, you have UTM machine. UTM machine you have to use to do compression strength and tensile strength test, fracture toughness. You might be all aware, you may be conducting your strength and material class to the students and your lab also. How you get material hardness, tensile strength, ultimate tensile strength, fracture toughness. You know the engineering stress, engineering strength for any material. how the stretching curve looks like for steel, mild steel, aluminum alloys, and so on. So basically, you have to qualify the material, their properties. I'm just talking about like mechanical properties, under static load, dynamic load, and so on. So once it provides good properties, then you take this properties input. Additively produced material, their properties is much superior. Sometimes it may be, comparable. Sometimes it may be poor, but that's where we to improve the properties further, we do post processing. Otherwise, I just want to highlight additively produced component. Their properties are much better than conventionally produced component. There could be exception, but it's always, as I mentioned, for Euro engine component, it makes sense to go for using additive route because we are able to control the microstructure of the component being produced. As I mentioned, well-defined microstructure is possible to produce with 3D printing. And again, when you go through, I am just taking the example of aluminum alloys. It is already used in aerospace application. And when you go through conventional route of casting or even through 3D printing also, I want to highlight, there is always a problem. Even if you use 3D printing technique for 2024 alloy, I am referring to aluminum 2024. I will also mention what is the composition in the subsequent slide. This alloy is used extensively in aerospace application. Right now, this alloy is being produced through a commercial route, through a casting route, followed by it undergoes several processing like rolling, forging, extrusion, and so on. And when it goes through casting route, there is always a solidification cracking, even if you go through 3D printing also. The first problem is solidification cracking. Second one, gas porosity. Third one is lack of fusion. Okay, the solidification cracking, why it occurs? The reason being the localized heating and rapid cooling. Typical cooling rate is of the order of 10.3 to 10% is second. Obviously, they provide favorable environment for solidification cracking. And this is one of the major reason we are not able to print different aluminum alloys like 6065, 70675. We always end up in seeing this problem because of very rapid cooling, differential expansion and contraction. You always end up in seeing there is a crack inside. This we call solidification cracking. Because liquid to solid transformation, solid to liquid, obviously because of very high cooling rate imposed, is a differential expansion contraction leading to the formation of the crack. Casting internally, you might have some cracks actually. One of the major issues. And again, there could be, for example, porosity also. Porosity also it could form due to complex phenomena associated with the laser powder itself. If you don't use appropriate laser energy source, we end up in seeing this kind of problem. Like, so for example, metal may evaporate also. That in turn will cause entrapment of gases actually. That's where laser energy density needs to be known for each material. Laser energy density is expressed as capital E equal to laser power P divided by scanning rate, hatch spacing. Hatch spacing is nothing but two adjacent beam. What is that? Distance. Two adjacent beam. What is the interlayer distance? That we call hatch spacing, and then layer thickness. All these three, used for a given powder. So if you don't account for appropriate laser power, rather I call it as laser energy density, so you end up in seeing the problem of porosity or even lack of fission also. Whether it may be under melting or it may lead to even vaporization also. So all these problems are encountered if you are not properly accounting for process parameters used in selective laser melting, or we can call it as laser powder bed fusion. So all these effects are seen if you try to print aluminum 2024 or 7074, 7075 alloy, because a very huge cooling rate being imposed to the material when you do 3D printing. We have seen the cooling rate also, it's of the order of 10.3 to 10.70 centigrade per second. Obviously, because of differential expansion contraction, you cannot escape the formation of crack when you go through 3D printing, even conventional casting route also. Okay, these are the problems. See, before I discuss about 2024 being 3D printed. Why I have to go for 3D printing 2024? Rather, my discussion is 2024 alloy. That alloy is added with titanium. That is the main focus of my talk today. Aluminum 204, if you do direct 3D printing, you encounter all these kind of problem. Even if you account for proper process parameter, you always end up in seeing due to difference expansion contraction, solidification cracking cannot be avoided. Maybe you'll be able to take care of lack of fusion gas porosity, but solidification cracking you are not able to take care when you go through 3D printing with the appropriate process parameter also. Then what is the remedy? That's what I'm going to discuss now. Again, before we discuss what we did with the 2024, how it is modified before we go for 3D printing. Before that, you look at this 2024, what is the specialty? And before that, you just look at this particular alloy composition I want to mention. Aluminium is a major principal element. What are the other alloying elements? You have copper, magnesium, titanium. Each series, 2000 series, 5000 series, 6000 series, each series is unique with respect to particular use case where you want to use it. Each alloy is unique in terms of what kind of property it can provide actually. I'm referring to 2024 is made up of major element is aluminum. In addition to that, we have copper, magnesium, titanium. Chemical composition also needs to be ensured. Something in excess is not going to be desirable at all for the properties. Not only controlling the microstructure, I need to have precise control over the chemical composition of the alloy also equally important. That is going to influence the final properties of the material, what you are going to 3D printing. Yeah. So just going back to application, you see that looking at the aircraft structure, where we can use this 202 for alloy. As I mentioned, in a typical the uniqueness of this particular alloy, it provides very high strength to weight ratio, tensile strength of the order of 400 to 470 megapascal. And also, it's a precipitation hardenable alloy. We are going to discuss the strengthening mechanism. Strengthening mechanism in the sense, why we are adding additional alloying element? Why not use pure aluminum? Pure aluminum cannot give the research mechanical properties. That's where we add a further alloying element. This alloying element, they end up in forming different phases, different precipitates. Those precipitates are contributing for strengthening the alloy. When I say strengthening the alloy, we want to improve the tensile strength. We don't want to lose the ductility. We want to have the combination of both strength and ductility, as well as you want to improve the fatigue life. If it happens to be under dynamic load, how the component is going to behave. That's why we're adding alloying element. Alloying element accounts for improving or strengthening the alloy properties actually. That's why I want to highlight. It is a precipitation hardenable alloy. Reason being copper and magnesium, they are going to form precipitate. That what we are going to discuss. You can see the wing part, spars, rib. They're all made up of using 2024 aluminum alloy. And also at the bottom, you can see leading edge. The wings and the fuselage parts in the aircraft, it is being made, fabricated by making use of aluminum 2024 alloy. And also, you see automotive application, truck wheels, it is being fabricated by making use of 2024 alloy. And then piston also, it's made, fabricated by using aluminum 2024 alloy. And again, as I mentioned, you always end up in seeing solidification cracking. You see the microstructure cracking if you do 3D printing of 2024 alloy. Is a major problem, as I mentioned, due to differential expansion and contraction. When solidification takes place, we end up in seeing the crack. You can see figure one. And again, if you look at through additive route, when you do 3D printing, we look at much bigger length scale, 50 micron length scale, we call columnar grain. It's all looking like pillar-like structure, columnar grain. Columnar grains also it doesn't provide desired properties, unlike, for example, eco-oxide grains. Eco-oxide grain means they have same dimension in all directions. Well-defined grain structure that you call eco-oxide structure is nothing but the grain shape, they have uniform in all directions. Size and shape is uniform in all directions. Yeah. So this crack component cannot be used for final application. When you go to 3D printing, you generally end up in seeing this cracking. Then how? What is the remedy? No? That's where we are going to discuss the motivation for this talk. We want to produce a high density aluminum 202 for alloy through laser powder bed fusion. The objective of this work, in fact, this whole work was based on one of my PhD students. He has spent almost 5.5 years because he joined during COVID period. He was able to produce this material defect free with improved static and dynamic properties. Having improved the properties of this alloy with the better static properties and dynamic properties, he was able to prototype 2024 alloy based engine mounting bracket. We got the design from NASIC, Indian Air Force from NASIC. We got the design for the brackets. These brackets are basically non-critical part. That bracket is basically used as engine mounting static brackets. It is basically supposed to take tensile load and compression load, basically sustaining the load of the whole engine. Engine mounting bracket, we got the design. Since we are able to do 3D printing of this alloy with the desired properties, we took this property as an input for designing the virtual prototype in order to make this engine mounting aerospace bracket. Right now, that bracket is basically Russian aircraft. All the design, everything, it was basically supplied from Russia. And through 3D printing, by improving the properties as well as by doing virtual prototyping, we were able to reduce the weight to nothing less than 20% weight reduction with improved static and dynamic properties. We always look for lightweighting. We went from material production to the prototype. We already made a virtual prototype. We are in the process of making real prototype engine mounting bracket that is in the process of printing now. Once you do 3D printing of the engine mounting bracket, we'll give it to NASIC, Indian Air Force. They'll be able to do field testing and then qualify the particular bracket. Once it is qualified, future, like we talked about Atmanirbhar, we want to make everything indigenously it's possible to make. It means that we start up the material, we establish properties through virtual. I was mentioning anything you can make through using simulation. Virtually, you can create anything. We made virtual prototype. Now we are in the process of, because we have all design details, process details. Now we are in the process of making the actual prototype. And once you do 3D printing, obviously, before you try to do mechanical testing, internal microstructure needs to be thoroughly characterized. I'm also going to discuss what microscopy we use it to understand the internal microstructural feature. Reason being, it is not only chemical composition of the alloy, we need to account for the internal microstructure. When I say microstructure, we are looking at internal grains or crystal size. Basically, you're all aware, any metallic material we call it polycrystalline. What do I mean by polycrystalline? It's made up of several crystal. When I say crystal grain, it means the same thing. Several grains aggregating, they end up in forming the microscopically. When you look through naked eye, it's a continuum. If we see through the microscope, it is basically heterogeneous microstructures. And again, we need to see, depending upon the alloy, we have to see whether it is a single phase alloy or two phase alloy, what kind of crystal structure it has. All such things are equally important. At the microstructural length scale, going from submicron to millimeter length scale, size and shape it matters. At the macroscopy level, if you look at any component, what kind of dimension it takes, that is going to influence, what kind of stress it is going to accumulate and so on. You have done rigid body mechanics, you do force balance. Okay, and strength of materials or deformable body mechanics, you always see, depending upon the complexity of the component, when it takes up the load, if it is going to deform, that we have to account. If it is going to deform its shape due to plastic strain, that we need to account actually. At the smaller length scale also, material also, I am talking as a mechanical person at the microscope length scale. I always look at any object, the dimension. What is the length, the breadth, the width, everything. Same thing you try to visualize at the material length scale, everything at the micron, submicron, and millimeter length scale. What is the internal grain crystal size looks like? Is it spherical, non-spherical, needle-like structure? I mentioned about lamellar morphology. It looks like plate-like structure. Each internal feature I look at as a mechanical person. What is the geometrical feature? Nah, you cannot say it's a metallurgy or microstructure. I'm just looking at smaller length scale, how they look like. I'm looking at the physical features. That's why it's called morphology. When I say morphology, as a human person, we say bulky person, slim person. Material also internally, I'm looking at what is the size and shape of the grain or crystal. Why I should care about it? Properties dictated by internal morphology of the material. Internal morphology of the material, size and shape I have to look at. That's why we always talk about metallurgists, they produce material, they do thorough characterization to ensure that material what we produce can exhibit desired mechanical properties. It's equally applicable for other properties also. You take magnetic properties, optical properties, electrical properties, all properties. These properties comes under functional properties. Electrical, magnetic, optical, magnetic, all these properties are called functional properties. For structural application, we are looking at load-bearing applications where mechanical properties are critical. We need to see how the microstructure is going to influence a property. That's why we are concerned with when you do 3D printing, the process is going to influence microstructure. Microstructure in turn is going to dictate the property. That's why we need to understand. Critically, we have to control microstructure. That's why it's called microstructural engineering of material produced by several routes. It may be casting route or it may be through 3D printing route. What I mentioned earlier was one of the unique feature of 3D printing technique. You are able to have precise control over the microstructure, what is being formed when you go through layer by layer deposition of material. Unlike in conventional manufacturing, you start with a very big chunk of mass that undergoes melting, solidification. You pour the molten metal into mold. It's a very big shape, actually. I mean, you cannot have uniform cooling from the surface to the bulk. That's why you end up in seeing heterogeneous microstructure. Surface may be well defined. If you go internally, across the cross section. The core will have segregated microstructure, rather we can say dendritic microstructure and so on. I'm talking about the huge variation in the microstructure properties when you look at conventionally manufactured part. Of course, we do further post processing also to make it homogeneous structure and things like that. We're just comparing one to one. How unique 3D printing technique compared to conventional additives being bottom up approach, they are able to have precise control over the melting and solidifications. Yeah. So methodology, we did 3D printing. In fact, sample also we printed in horizontal direction as well as vertical direction. And then we gave post processing heat treatment also we gave. So any material being produced by different route, we have to look at as fabricated sample, followed by if it requires post processing, we need to do. Predominantly, we play with the heat treatment. Most of the conventionally produced material, we always play with the heat treatment also in order to improve the properties further. So once you give the heat treatment, again microstructure also undergoes transformation. We can control the size and shape. This I call microstructural engineering of the material as fabricated sample, followed by if you do post processing, we can control the microstructure. Obviously, when you give heat treatment, microstructure they will undergo transformation. This we call phase transformations actually. So it's possible to tune the microstructure. As a result, we'll be able to end up in getting the desired microstructure to give record properties. So post processing, and then for the 3D printed sample, we did the NDT analysis through X-ray CT scan was done to see whether there are any internal defects in 3D printed sample or not. And then having done thorough characterization for the us printed sample upon heat treatment, followed by analyzing the internal defects by using X-ray CT scan. All the 3D printed sample, I mentioned it like 3D printed test coupon. It went through all the testing, tensile test, hardness test, fracture toughness, fatigue crack growth rate, fatigue life, and of course, microstructure characterization, you can use XRD, and we have EBSD, electron basket diffraction. Again, I will discuss how the feature size looks like if you do EBSD. We have TEM, transmission electron microscopy, scanning electron microscopy. All these techniques were used to characterize physical features of material, which is 3D printed actually. Of course, we did FEM simulation also for all the properties. FEM simulation and XFM simulation is unique technique if you want to account for discontinuity in the material. It may be crack or discontinuity in the material. You don't require any mesh refinement is not required. Okay, remeshing is not required. If you make use of the XFM technique I will not cover right now. I will only want to discuss how we did 3D printing, their mechanical properties, how they look like, as printed sample, and then post process sample. And we went through characterization to look at their internal microstructural features that internally related to the properties actually. And again, what I mentioned was like, figure two for alloy, you have problem of solidification cracking. What we did in our work, we added 2% titanium to the starting alloy. Aluminum 2024, I already mentioned their composition. It is having aluminum, copper, just going back one second. It has aluminum, copper, magnesium, manganese, titanium, silicon, Fe, and aluminum. You can see their composition also. Powder composition is given. Once you do 3D printing, their composition is also given. And the bottommost is conventionally made 2024 alloy. For that alloy also we compared what is the chemical composition. Yes, we should know precise chemical composition as well as their microstructure also. See, this original 224 alloy ends up in giving solidification cracking. What we did, in fact, we procured this powder. Aluminum alloy plus 2% titanium has been added. By adding 2% titanium, in fact, you can look at the esteem ratio. Hope you are able to see the slide. You can say yes. I'm changing the slide. I want to ensure whether you are able to see the slide printing. Figure 1.
Yes, sir. Yes, sir.
Yeah. So you try to see extreme left and extreme right. If you use pure aluminum 2024 alloy without adding titanium, you have columnar-like structure, pillar-like structure. And you can see in between two columnar grain, you have the groove, you have the shallow groove. That is the one being culprit for inducing solidification cracking. But if you use titanium 2% to the aluminum 224 alloy, it is refining the microstructure. So-called eco-oxide structure is spherical. They all same dimension, all direction. So the cavity, the groove is completely filled with the model metal. Okay, we end up in getting eco-oxide structures. So it's able to take care of solidification cracking. So titanium is acting as a very good grain refiner. So 2% titanium added aluminum 2024 alloy. If we do 3D printing, we are able to overcome the solidification cracking. That's what we want to highlight. 2% titanium has been added to aluminum 202 alloy. Starting alloy powder itself, it contains 2% titanium that is acting as a grain refiner. That's why we mentioned bullet point. The columnar grains have deeper grooves between them, leading to higher susceptibility to cracking. And epoxy grains have smaller groove. They result in very, very low solidification cracking. So how to take care of solidification cracking? We added titanium as a grain refiner. As I mentioned, during solidification, liquid to solid transformation, it's possible to control the microstructure what is being formed. I already mentioned columnar structure, epoxide structure, laminar structure. There are different morphology. I'm again referring to going down the length scale from millimeter to micron, submicron. The internal microstructure, I'm looking at the physical feature, size and shape of the particular grain or crystal. The epoxide is being desirable to do 3D printing of titanium added aluminum 2024 alloy. The role of titanium, it is able to modify the grain shape from columnar to epoxide structure. The metallurgists, they study in detail solidification kinetics of different alloys. They play with the nucleation kinetics. You're all aware about thermodynamic heat transfer also. We talk about nucleation and growth. Same thing during solidification also. They discuss in detail. It all comes under physical metallurgy. Metallurgy, they spend no, or they study exclusive course on solidification kinetics of different alloys, how we can transform from columnar to epoxide, how to play with the process condition so that you get desired microstructure and so on. So what we are trying to highlight, we used 2% titanium and aluminum to for alloy. So when you did 3D printing, it's able to take care of solidification crack. And again, having 3D printed, so as I mentioned, the as-built sample, we have to characterize the properties. Of course, we need to characterize the microstructure and post-processing. As I mentioned, any as fabricated sample being 3D printed or through conventional manufacturing, it needs to be subject to further post-process heat treatment. We want to fine-tune the microstructure further. That's why I call microstructure engineering through post-processing. It is like heat treatment. So we did heat treatment post-processing. What it did in order to improve the properties of the alloy further, you can look at this temperature versus time. Basically, we are given TCS heat treatment. What does it mean? It means that 3D printed sample is subject to the solutionizing treatment. If at all, if you end up in seeing any heterogeneous microstructure, we want to homogenize it. If at all any undissolved precipitates are there, you want to dissolve it in the solution. That's why it's called solutionizing treatment. At 493 centigrade for 1 hour, it's able to produce homogeneous microstructure. Having done solution treatment, subsequently it is subjected to aging treatment at 190 centigrade for 10 hours. When I say aging treatment, through this particular temperature and time treatment, through aging process, it tends to evolve precipitate from the material. When the precipitate comes out from the matrix, the precipitates are going to contribute for improving the strength, the ductility, as well as fatigue properties also. We are going to see in future slide, aging treatment has caused the evolution of the precipitate from the microstructure. That's what we are trying to highlight. So purpose of doing heat treatment, we want to ensure microstructure has been engineered or fine-tuned to end up in getting improved mechanical properties of the 3D printed alloy. Just by doing 3D printing alone, you may not be able to get record properties of the printed material, printed material. That's why we are doing post-processing. Why I have to post-processing? I want to fine-tune the microstructure to improve the properties further. Hope it's clear why I'm doing post-processing. And again, the before we went for 3D printing, the starting powder itself, we characterized it. I mentioned powder needs to be qualified before you go for 3D printing, looking at the microstructure, looking at the chemical composition. Chemical composition was analyzed by making use of X-ray fluorescence. Okay, and then the to qualify the powder size and shape, you can look at the particle size distribution of the powder. That's where the size and shape of the powder, you always prefer narrow size distribution. It should not be like no, some particles, powder particles are 10 micron, some powder particles 100 micron. Okay, that is not going to be helpful. I need to maintain narrow size distribution of the powder particle to ensure that because it is going to affect the melting characteristics. Time and taken solidification characteristics actually I mean. Okay, in order to fine tune the solidification kinetics, I need to have the appropriate material which is already been qualified where it is not possible to do 3D printing of such a powder. Their flowability, they try to characterize the powder size and shape. That's why it is given already. Not only chemical composition, we did a thorough characterization of size and shape also. So micron size, we can do SAM also. Okay. So chemical composition is through X-ray fluorescence. You can see their composition. Topmost is for powder. The middle basically 3D printed alloy, and the last one is conventionally produced aluminum 224. And again, powder also look at, yes, we characterize the powder thoroughly. We are not just not taking the powder directly for 3D printing. Qualify the powder, whether it gives appropriate chemical compositions and size distribution, everything we thoroughly characterized. What is SEM micrograph actually? SEM micrograph. And also you can see here, figure 1A, you can see morphology of the powder particle, and then extreme right also particle size distribution, and the elemental mapping at a given location, what is the composition? That also we did through X-ray fluorescence actually. Where is different color you can see, where aluminum is being found, copper is being found, titanium is being found, magnesium is being found. We have done complete mapping, complete characterization of the powder itself to begin with, before we went for testing the 3D printed sample. Again, you are all aware, how we do harness testing, tensile test. We have ASTM standards. Okay, tensile specimen, how we can have rod sample, plate sample as per ASTM standards actually. I mean, if you want to do a pressure temperature test, you can go for using 3-point bend test, or you can even use CT specimen also. And again, sample is being fabricated, vertically built or horizontally built. The orientation also it matters. Different orientation of the printed sample. Okay, that also we used it. No? Tensile sample were printed in vertical direction as well as horizontal direction, because we want to know whether orientation is going to be matter for the final properties of the material being 3D printed actually. So we went through the all this testing, different test coupons were made. Okay, and the defect also we analyzed through X-ray diffraction, X-ray CT scan. Internally, if you have not accounted for proper process parameter to do 3D printing, I would like to highlight once again, laser energy density is expressed as capital E is expressed as laser power P divided by scan speed, at what rate you're scanning the laser over the powder. And then I mentioned about hatch spacing. We have laser beam. Two adjacent beam, what the distance actually mean? Whether you're using lower hatch spacing or higher hatch spacing, that is going to matter a lot connecting you to deposition rate actually. And then the layer thickness. I mentioned in the laser powder bed fusion, the brick platform, you lay one thin layer of powder. You need to know what is thickness of the layer. Thickness of the layer, laser scanning rate, and then the hatch spacing to adjacent laser beam. I'm referring to the laser beam, their spot size actually. I mean. So that also hatch spacing also plays a role to see what is the appropriate energy density should be used to do 3D printing of your material. Each material, we know their melting, we know their characteristics in terms of how much laser it can penetrate when you try to shine it with the laser of, we use different laser power actually, depending upon the material. For high melting alloy, we use very high laser energy source. Low melting alloy, we should use less power actually. And again, if you don't use appropriate laser energy density, you end up in seeing either over melting or under melting. That's why we talked about over melting, it may vaporize. That may result in forming entrapment of gases. We always talk about when I say defect for the 3D printed part, you can have mechanical pores due to gas entrapment or even metallurgical pore also if you don't take care of proper process parameter to 3D printing. So these internal defects, why we use X-ray CT scan? The internal defects is not visible to the naked eye. It may be micron size pore or even millimeter size pore. Millimeter size pore you can see through naked eye. If it is micron, submicron, I have to do X-ray CT scan to analyze internal defects. Once again, when you do 3D printing, what is the final density of the 3D printed part? It cannot be 100%. Because powder is undergoing melting, solidification. If you are not accounted for proper process parameter, even accounting for optimized process parameter, the density can never be 100%. There could be always internal defects, minor porosity content. That also needs to be analyzed through X-ray CT scan. Will come to know whether they have poorly packed 3D printed part. What are the internal defects? For which you need to do thorough scanning through X-ray. 3D printed material should undergo thorough scanning through X-ray. Please see what is the defect, not only seeing the presence of defect, what is the quantity of defects actually being present and how they're distributed. That also needs to be quantified for 3D printed materials. And again, going in depth to see that what is the density for the 3D printed part being vertically built, horizontally built. That is also being given here 19.85, 19.72. And what we're trying to say that with respect to different orientation, horizontally built sample and vertical built sample, we try to highlight that the lot of defect is being found in horizontal sample compared to vertical sample. That again we try to relate to thermal gradient. Obviously, cooling rate, how the heat dissipation occurs, that matters a lot depending upon whether it is being vertically built or horizontally built. We are trying to highlight horizontally built sample has a lot of defects due to thermal gradient compared to vertically built sample. The way the heat is being dissipated when it undergoes controlled solidification from liquid to solid transition. Yeah. And again, this slide to show you, in fact, I mentioned about defect. You already did 3D printing. I want to look at microstructure. So what is being seen in the extreme left, you could look at the bottommost. In fact, this is basically called electron vascular diffraction. It is nothing but camera. It is nothing but camera. It is attachment to scanning electron microscope. Using this EBS as a camera, I am able to visualize the so-called internal microstructure, which is made up of several grains or crystal. What is that you end up seeing the extreme left? How they look like? You can see the extreme right side bullet point. What is being given? If you are listening to me, at least one of you can say, looking at physically, visually how they appear like extreme left. Some of you can unmute. I want you to interact. If you are with me, if you are able to connect with me, what I said so far, the 3D printed aluminum 202 alloy, having added with the titanium, if I see through EBSD camera, the internal microstructure I mentioned is made up of several grains of crystal. You have several colors. What does it indicate? What is the size? You can see that. You have well refined, they call ultra fine grained microstructures. The size varying from 0.401 to 0.434 micron. You can see at the bottommost, the EBSD is nothing but electron basket diffraction. We look at vertically built sample and horizontally built sample. The figure A represents grain size color orientation map. B represents each grain is having its own orientation. That's why we want to quantify how many number of grains are with a particular orientation. The figure B gives misorientation angle. C pole figure. Again, we want to visualize using the pole figure. I want to look at the typical grain size graph. Extreme right. What the typical grain size? You see several grains, thousands and thousands of grain. I want to quantify that grain size distribution. So which size to which size you see? You cannot have a very wide grain size distribution. That is going to be detrimental for the properties actually. I mean, look at the microstructure through the camera. Look at their orientation. Through pole figure analysis, I want to get microstructure being produced through 3D printing. What is the grain size variation? From what size to what size it varies. It is not desirable to have very wide size distribution for the grains also. Like I discussed about powder particle size, the 3D printed material also, when you see through a microscope, they're all interconnected grains or crystals. What a typical size and shape that is being characterized through EBSD microscopy. Then it's called camera attachment to scanning after microscope. Again, to ask you, why should I care about microstructure? Anyone can tell? The microstructure is completely equi-oxide. Ultra fine grain microstructure is due to addition of titanium acting as a grain refiner. You tend to see orientation of course, we tend to see there is no anisotropy. You're all aware about, we talk about isotropy, anisotropy. Anisotropy is not found. No, they're all having the random orientation of the grains actually. I mean, this you call texture. We can study the texture, anisotropy of the material also. Looking at the internal grain size, shape distribution, and the orientation also. You end up in seeing random distribution of the grains and what size it takes, that is also being given there actually. Why it should matter? If I ask you, any one of you, why should I care about seeing the grain size, shape, orientation? Again, this was 3D printed as-built sample, 3D printed material. Titanium added 202 alloy. And again, heat treated. Again, looking at microstructure. So, such a beautiful microstructure through EBSD camera. Look at again. Again, we are looking at what happens if you do heat treatment. There is going to be always microstructure transformation. For example, average grain size increase slightly. And again, we try to highlight horizontal specimen grain size is slightly lower compared to vertical sample. And then we want to look at the typical orientation of the grain. We call high angle grain boundaries. Yeah, each grain is separated by boundary called grain boundary. That also we want to characterize what is the volume fraction of high angle grain boundaries and low angle grain boundaries and so on. That is also we are saying with the heat treatment, what is happening to the horizontal build sample and vertical build sample. And then if you do X-ray diffraction, you can see at the bottommost. We have seen the physical features. As I mentioned, the alloy containing aluminum plus other alloying element. They have the powder. We did 3D printing. 3D printed sample, we have to do X-ray diffraction to see what phase it shows. You all know the meaning of phase. We have solid phase, liquid phase. No, it may be vapor phase. No, for ice is solid. It undergoes melting liquid, and if you boil it, it goes to vapor state. Solid state, liquid state, vapor state. We call it as a phase. Within the solid itself, we have seen the microstructure. What is the morphology? When they mix up with each other, how many phases they end up in forming? Is it going to be single phase? It will have only one single crystal structure. When they say two phase alloy, the two phase will have different crystal structure actually. The way they mix. In fact, when you add alloying element, to what extent you can keep adding? They end up in forming alloy or solid solution. There is a limit beyond which they end up in forming another unique phase actually. That's where here we end up in doing X-ray diffraction right from the beginning of the powder, and then we did as-built sample, 3D printed sample, vertically built being 90 degree, horizontally built being 0 degree, and the heat treatment also we did for both samples. And what we saw, what is the phase observed? The primary element for this alloy is aluminum that is being indexed in this particular X-ray diffraction alpha phase. And then having alloying element like copper and magnesium, we end up in getting unique peak for the presence of precipitate, that is Al2Cu precipitate, that we call theta, that is having particular crystal structure. That's where we use the particular theta symbol for Al2Cu. And having copper and magnesium along with aluminum, we end up in seeing the formation of precipitate, that is Al2C magnesium. That phase is called S phase, plus titanium precipitate also. So what you want to highlight, in order to get very good static and dynamic properties of this titanium added aluminum 224 alloy, we are seeing the role of alloying elements such as copper and magnesium. Theta phase and the S phase, they are the main strengthening precipitate in aluminum 2024 alloy. Again, why should I care about composition? Why should I care about microstructure? Properties of the material is dictated by what kind of phase they tend to form, what kind of precipitate they tend to form. Precipitate plays a major role. And again, looking at precipitate, what precipitate is formed, contribute to strength. You are all aware about if you have soft edge corner, it is going to act as a stress raiser. Same way, if you don't control size and shape of the precipitate in the material, that is going to act as a stress raiser. That is going to be detrimental for the component what you are going to make. Any component when it fails, the root cause analysis we do, how the component has failed. Is it due to design or is it due to material the way it was being fabricated actually? Very often we end up in saying the material microstructure was not properly controlled. Precipitate role was not accounted properly. Precipitate was not properly sized. Rather than having spherical precipitate, you are having needle-like precipitate. If you have needle-like precipitate, that is going to act as stress raiser. And stress raiser is going to be detrimental. For example, if you have crack having precipitate being needle, that is going to act as stress raiser. That means what stress will accumulate at a very rapid rate actually. So we need to prevent. We need to control the size and shape of the precipitate, not only precipitate, as we discussed, the overall grain size also for the material what is being formed. So the theta and the S precipitate, they contribute for strengthening mechanism. And again, we want to highlight that for post-processed and heated sample, okay, we tend to say that the intensity of the precipitate, okay, it has evolved in size and shape by giving heat treatment. Titanium also was observed, but they were observed in the form of pure titanium, not in the form of compound like Al3 titanium precipitate were not observed, of course, in our study. And again, look at here through scanning under a microscope. Again, what you see, whether we get any signature for presence of titanium. SM, it was not giving a detailed picture. And by doing TM, we are able to identify. The transmission electron microscope also another technique wherein we can go much deeper length scale. We can look at nanoscale pictures, even at atoms length scale, nanometer length scale. If any precipitate spaces are being found, we can detect it through this particular transmission electron microscope. Again, having mentioned like it tends to form theta precipitate and S precipitate, their typical precipitate size is almost submicron size. That's what we want to highlight by doing TM. We did for as-built sample as well as for heat sample also. Their size and shape tend to change the precipitate. We characterize the precipitate being formed through SEM and TM to look at morphology, how they look like. And again, having done a complete tensile property and hardness property, what I want to conclude, if you look at, you can see extreme left. Hope this slide is visible for all of you. I will complete in another 10 minutes. Hope you are able to see this slide. Hope all of you are with me. I hope you are able to follow me.
Yes, sir.
Just to reference and recap. Okay. Even some of you could not follow what I said. I just highlighted how to produce 3D printed titanium added aluminum 2024 alloy. What is the role of titanium? The titanium is acting as a good grain refiner. Starting powder itself is being taken care whether it is 3D printable or not. So the titanium added aluminum 2024 alloy, when you use it for 3D printing, I end up in getting well refined microstructure for 3D printed sample. Having done 3D printing, the sample needs to be characterized right from X-ray CT scan, X-ray to see several phases, scanning electron microscopy, TEM, all such characterizations required to look at internal physical structure of the grains or crystal which makes up the whole material. If you see through naked eye, everything is continuous. I am giving another analogous example. Blood is a liquid, and when you see through microscope, what does it contain? Do you have solid particulates in blood sample? Any of you can you tell? We talk about red blood cell, white blood cell. Do you have solid particulates in blood samples? Anyone? I'm highlighting about physical features. Always say cell, no? Biology, we always talk about cell. I want to know whether blood, no, blood is being, you can say, non-Newtonian fluid. Does it contain any solid particulates or purely liquid only? Just think about it. I'm just trying to highlight what I discussed so far, going through 3D printing, use appropriate process parameter. And again, just before moving further, why should I go for laser? Why not ordinary light? Anyone? The whole audience? Maybe we can take up the questions at the end. Just to highlight what you see in this particular stress strain curve, we want to highlight for us build sample is being AB, HD is horizontally built sample. What we want to highlight, the tensile strength and hardness. To generalize, the heated sample provides better properties compared to us built sample, even as compared to conventionally prepared physical to flora, they provide better properties for us built sample as well as for heated samples. And again, for having done tensile test, we want to understand what is the mode of failure. So we have done thorough, this we call photography. Any failed sample, we want to understand the microstructural mechanism. What has contributed for the failure of the sample? We have done thorough photography. That can be done once again by using E-based camera as well as by FEM also. And we did a 3-point bend test to study the fracture toughness of this particular 3D printed material. We are able to show for heat-treated sample, it provides better property. There we try to use a term called fracture toughness KQ and the J integral. J integral takes care of how much process strain material can take. That indirectly dictates what would be the fracture toughness of the 3D printed sample as well as for post-process sample. What you want to highlight, you can again see from this table, heated sample provides better fracture toughness. And we are comparing, in fact, just to highlight of this whole discussion, what you see from this table, 2024 alloy, okay, the current alloy and produce the other route, 2024 O, T3, T35, all these O, T3, T351 refers to different heat treatment. We have compared material produced to 3D printing, current work, in our work, titanium added aluminum 2024 alloy, you look at their yield strength, ultimate tensile strength, typical strain, how much it can take, hardness and fracture toughness. We have compared our 3D printed alloy with a conventionally prepared alloy. You can see from this table. And again, this slide also to compare additively prepared 202. I have to benchmark. Just doing printing, characterizing, reporting has no meaning. What I produced, compare it with what is already known. That is being shown for this particular slide. You can see yield strength, ultimate tensile strength, hardness. Everything is being depicted here. And numerical simulation I'm not going to cover, discuss right now. And again, we did fatigue life also under cyclic loading. In fact, you are aware about any moving parts, rotating parts. We need to thoroughly characterize their fatigue life, high cyclic fatigue and low cyclic fatigue. Number of cycle under cyclic loading. If it's greater than 10 we call high cyclic fatigue. If it is less than 10 we call low cyclic fatigue. To characterize high cyclic fatigue, we use this Baskin model. Rather, we try to highlight stress versus number of cycles to failure. You can see from the figure 1, SN curve is nothing but stress versus number of cycles to failure. Having plotted your experimental data, I fit into using Baskin power law model. Stress amplitude that is being connected to sigma f is fatigue strength coefficient. N is nothing but number of cycles. B, it represents their strength exponent actually. So we have the value P and sigma F having fitted this estimated data to this power of fit actually. It basically we are quantifying high cycle fatigue and extreme right side also to show that heat treated sample. So heat treated sample we want to highlight in fact the fatigue life of heated sample is better compared to the as-built sample. Yes, due to microstructural refinement or transformation, we are trying to see the extreme right side picture. Heated sample provided better fatigue properties. And again, see stress versus number of cycles to failure, stress versus number of cycles to failure. Look at the loading pattern. We use the term when it comes to fatigue life, you should know what is stress amplitude. Sigma max minus sigma minimum by 2. This we call stress amplitude. Rather, you need to understand the different terminology when you want to study fatigue life. What I mean by mean stress? Mean stress is nothing but sigma max by sigma minimum. You are applying the load maximum to minimum. Sigma max by sigma minimum by 2, that is mean stress. And stress range is difference between sigma max and the sigma minimum. Stress amplitude, we try to highlight sigma minimum minus sigma max minus sigma minimum by 2. That is stress amplitude. Stress range also capital R, sigma minimum to sigma max. Rather, we want to look at the loading pattern to the parts. The top one, when you do fatigue testing of any material, you need to have understanding about all this term. Mean stress, stress range, stress amplitude, stress range, capital R. Look at the different loading pattern. If it happens to fluctuating stress, R is greater than 0. If it happens to be repeated stress, look at R equal to 0. Having defined what is stress range, sigma minimum to sigma max. If it happens to be reverse stress, look at the R value. We do fatigue testing of the sample with respect to R value, what is being kept actually. The loading pattern could be periodic. Even you can have loading pattern with a variable loading pattern with variable amplitude also. Variable amplitude also. So we are trying to highlight the role of this mean stress, stress range, stress amplitude, and stress ratio that is being stress range or if we have to account the loading pattern is fluctuating stress, repeated stress, and reverse stress. When I say reverse stress, what is the plus sign minus sign indicates? You will have tension, okay, or tension compression or compression. So load pattern being dynamic and a dynamic loading, when the load is acting on the sample, is it tension or tension compression? Loading pattern you should know. That's where we are trying to characterize in terms of fluctuating stress, repeated stress, and reverse stress, and so on. When you do the fatigue testing of the sample. And again, fatigue tested sample also through photography, if at all internal cracks are being present, how they tend to move under cyclic loading. That also we did thorough characterization for the fatigue tested sample. And we have seen that fatigue properties of heated sample is much better. And again, the previous one is just assuming you are applying the load under dynamic conditions. Load could be tension, compression, or combination of both. We have never accounted inherently the presence of the internal cracks. The moment if you have crack inside the sample, I mentioned it might have pore or cracks inside the material, for which you need to understand the role of cracks or flaws being present in the material. That's where we need to do fatigue crack growth studies, for which you can make use of CT sample, combat tension sample. Again, by using ATM machine, you can apply the load. We continuously track the growth of the crack, how they move across the cross section of sample. That's why we use Paris law. The dA by dN it represents A, it represents crack length, how the crack size is growing as a function of number of cycles actually. That is being captured through Paris law. You can look at the extreme right side picture. We want to quantify the crack growth rate as a function of, you can see delta K. Delta K, it accounts for stress intensity factor actually. So that is being plotted. We have several zone, threshold zone, and middle region is called Paris zone. Third one is final failure. The crack growth also goes through several stages. Non-linear at the beginning, linear at the middle, non-linear at the end actually. The middle portion is being captured accurately by using Paris law actually. We want to understand at what rate crack is moving. If it happens middle sample, obviously crack will move very fast under dynamic load condition with less number of cycles, the sample will fail. Okay, that's where it is important to understand crack is being present in the material. We want to see load is being applied dynamically due to tension compression, how the crack is moving. As compared to the grain size responding to the applied load, the internal crack, they will tend to respond faster. The crack is moving across cross section. When they move fast, when they move to the cross section of the specimen, obviously you end up in saying sample is breaking into pieces actually. So the middle region is able to capture accurately by using Paris law. For nonlinear, at the beginning, at the end, we apply Paris law actually. And NASGRO, once again, this model developed by NASA, they are able to account the influence of stress ratio much more accurately. That's where right from beginning to the end, it's able to capture at what rate crack is growing in a given sample. That also it's by NASGRO model also we did analyzing the estimated data through this particular NASGRO model. And again to compare for heated sample and husband sample, we applied both Paris law and NASGRO. NASGRO is able to predict at what rate crack is growing. Extreme right side to highlight crack growth rate versus stress intensity factor. What you want to conclude, heated sample provide better properties. Once again, we are comparing with the conventionally produced wrought aluminum fluoride alloy. We want to highlight the fatigue crack growth resistance of 3D printed sample is poor compared to the wrought alloy. And again, we want to highlight 3D printed sample followed by post processing. They try to provide better fatigue properties compared to conventional wrought aluminum 2024 alloy. Again, here this to highlight internal porosity, how the cracks are moving. I will not go in depth into this particular micrography. We have done XFM simulation for crack growth movement also we characterize. Not only doing experiments, we did thorough simulation also. For XFM, the beauty of XFM, it takes up discontinuity in the material. The crack movement, you don't require any intensive mesh refinement. You don't require, remeshing is not required if you go for using XFM. If you ask me what is the uniqueness of XFM, you are able to use unique function. If you have done FEM course, we talk about shape function. We are using special function. When you try to do FEM modeling of the particular specimen, we accounted for discontinuity by introducing special function to account for the discontinuity. That's where we don't need to do continue remeshing of the object, having done meshing through particular meshing software and so on. So I will not go. And again to conclude, we are able to produce ultra fine grained microstructure by using titanium modified aluminum 202 alloy through 3D printing. We are able to prove it's providing better tensile property, fatigue property as compared to conventionally produced aluminum alloy. Having established properties, we have done virtual prototyping of engine mounting bracket for aircraft application with a significant weight reduction without compromising properties. Rather, we were able to improve static property as well dynamic properties also. Now the design is known, process parameters are known. We printed 3D printed sample, qualified properties, and then we did virtual prototyping also. Now we are in the process of making the actual prototype before it is being put into use to test it in the actual field actually. Once again, the typical bracket is non-critical part. We can easily test it and qualify. We can go for making it indigenous within India. Yeah. So with that, let me continue, conclude. And again, the whole work, I would like to thank one of my students. His name is Dr. Saurabh Goyrala. He has published around 6 to 7 papers. Plus, he has filed a patent also. Titanium modified aluminum 2024 alloy. He has already filed a patent also. Virtual prototyping also. We are in the process of filing patent now. Once you make the real prototype, once it is getting qualified, we can go for another patent also. So whatever we do, we want to take it from material to the prototype and where it is going to be used. Not only publishing paper alone. Need of the hour, we need to focus towards developing our own indigenous components for our own Indian use. We cannot keep importing from abroad. India is putting a lot of emphasis for core, mechanical, civil, electrical. They are equally as important as computer science. Just by knowing coding alone, it cannot help. Being a mechanical engineer, you can do wonder. You can produce machine, you can produce prototype. Sky is the limit. If you want to interact with me further, I can give thousands of ideas. If you are motivated, thousands of problems are there. If you are aware, we talk about IoT, Industry 4.0. Without mechanical, nothing can be done. Just by pure computer science alone, it cannot do wonder. Most of the college, they are doing damage by removing mechanical field, by not having appropriate curriculum. They are diluting mechanical. Future, there is going to huge vacuum in mechanical field, electrical field, and civil field for all your information. Most of you are coming from colleges, you have to sensitize, you have to give awareness to the students, parents, to say that if you are having employable skills, if you are able to use engineering software properly, you can design and develop any damn thing virtually in computer. That's what industry is looking for. Employable skills in your own field. You should be capable of understanding FEM. You should be capable of doing virtual prototyping of any component in computer. Without that, where is going to be job for mechanical engineers actually? That is happening. That is happening already. having computer science thousands of candidates and mechanical only 40 students, 30 students. That is not going to be helpful. Already people started realizing, bring your AI tool, bring your software skills. You have to be good at FEM. Okay. The uniqueness of IIT NIT is they have flexibility to do a lot of electric courses. They may be doing a lot of AI-based courses, CS courses. They may be doing data center algorithm also. Being an IIT, even metallurgy student, mechanical student, they get very good job. As good as like computer science students. Okay, there are enough challenges. Okay, we cannot say that mechanical field is dead. It will never die. It's all our poor awareness about mechanical. We highlight that CS is superior, EC is superior. Each branch has its own important significance. Maybe let me stop. We can interact more actually.
Thank you, sir.
Yeah.
Sir, already our another guest is also joining Shreyas Potential.
Yeah. So any questions, please, you can ask me. You can unmute also. I would like to answer.
So some of the questions I posted in the chat box.
Yeah.
So
Yeah. So the first question, is it possible to simulate the process parameters of new 500 rupee alloys? Additive, why not? In fact, there is software called Sumu Factor. For 500 rupee alloys also, when you do through 3D printing, we can do process simulation, we can do design simulation, even you can do property simulation also. Okay. And second question, is the heat treatment record additively manufactured 500 rupee alloys like conventional method? Of course, from material to material, obviously it requires post-processing heat treatment also. You cannot directly use it. Of course, number of post-process treatments are relatively less compared to conventionally produced parts. Third one, uh, what is third one? Is a miniature prototype valid compared to the full size? Yeah, it's valid. You have to look at what final prototype dimension you look for. Accordingly, you can always scale it. You are having the replica of the massive part. You are just scaling it down. To the simulation, you can scale it up also. What's the problem? There's no problem. And the last one, making the powder for hydropy alloy. So it's possible to produce a hydropy alloy powder also before you take it for doing 3D printing. Making powder for new hydropy alloy, it's possible. You are aware about rapid solidification due to automation, gas automation. So the gas automation process, the way you do the rapid solidification of your molded metal, it can ensure the formation of hydropy alloy. It's possible to produce by playing with again process condition utilized for rapid solidification of your molten alloy to make hydropy alloys actually. We say inert gas automation. Again, you have to bring fluid mechanics. At what rate you allow the molten metal undergo solidification. You can critically control all the process condition corresponding to the alloy what you want to melt and solidify actually. Yeah. So anisotropy also is inherent. For example, if you take HCP alloy, obviously you will end up using anisotropy. Anisotropy also can be tuned. Again, the way you do the scanning by using laser actually. Can I able to see the chart? Yeah. So Abhirami is asking, she is not able to see. Yeah. So overall, I highlighted for high end alloy is possible. We can do process optimization, design optimization. In fact, for information with the advent of AI tool, it is possible you can fix the outcome. I can give the what should be the input variable. It may be for your design, it may be for process, everything can be optimized. This is called inverse problem to do design optimization, process optimization.
so these are the
The take
questions
home
we
message
received
for
from.
our college, you have to offer APM course as a core course. You have to expose them to coding. You have to expose them to AI tool. Okay, with all this exposure to software plus the AI tool, plenty of scope in our own domain. That's what I want to conclude.
Sure, sir.
Yeah.
So these are the questions from our audience. So
Yeah.
if due to time consideration, we are limiting the question. If you have any
Yeah, please,
questions,
please.
you
And
post.
you can, please, Dr. Vinod, you can share my email ID to them. They are
Sure,
most
sir. I
welcome
will
to
share.
interact with me. They are most welcome to interact with me.
Sure, sir.
Yeah. In fact, for your information, they can visit our IIT also. We have a metal printer, 3D, three machine we have. Three metal printer we
Sure,
have.
sir.
polymers, we have nothing less than 15 printers. If they want, they can come and see the facility over here.
Okay, sir.
Yeah.
So, on behalf of our organization and all the participants, I will take this opportunity to sincerely thank our esteemed resource person, Professor Dr. R.Jayaganthan sir, for delivering such an insightful and engaging session today. Your expertise, valuable inputs, and practical perspectives have enriched our understanding and made this session truly meaningful, sir. We are grateful for your time and effort, for your dedicated to be with us, for sharing your knowledge. Once again, I'm thanking you, sir,
Yeah,
for
thank you, Dr.
providing
Vinod.
this
So once
opportunity.
again, I thank all the participants for listening to my lecture. You're most welcome to write email to me for any queries. Okay.
Sure, sir.
Okay. Thank you once again to all the participants. And I request Dr. Vinod, you can share my, I will send this PDF file of my presentation. You can send it to all the participants actually.
Sure, sir.
Okay. Thank you. Hope I can sign off.
Thank
Once
you, sir.
again, thanks to all the participants. Thank you so much.
Sure, sir. Sure, sir. Thank you, sir. So it's time to start our second session. So it's my due. No, sir. Swain, sir.
Yeah,
Hello.
good evening, all of you.
Thanks, sir. So sorry, sir. Sorry for the delay. So it gives me a pleasure to introduce our next team, esteemed speaker, Shreyas Kotal, sir. A seasoned professional with 13 years of rich experience in the field of new product development, defense, and aerospace product development, material characterization, quality materials, and additive manufacturing. Mr. Kotan is highly skilled in areas such as metal additive manufacturing, reserve engineering, IP management, and design for additive manufacturing, laser physics, machine building, and machine business development. His manufactured experience has made a significant contribution to India's to achieve manufacturing ecosystem. He has spent nearly 12 years at Bharat Forge Research Development serving in a various strategic role where he was deploying now in a cutting edge R&D activities. For the last 3 years, he has been associated with Amadeus Productions Bangalore. We are pleased when he played a key role in developing India's first metal 3D printing machines, a remarkable achievement in the country's manufacturing innovation landscape. Mr. Ketan holds masters from M.Tech in material manufacturing and modeling science from prestigious institution, Indian Institute of Technology, Bombay. We are honored to have with you, Esther. We are we are looking forward to gain valuable insight forms in vast experience in additive manufacturing and product innovation. We are welcoming you, sir, for this session.
Thank you, Professor, for the nice introduction. Am I audible, all of you?
Sir, you are audible, sir.
Okay. So, shall we start the presentation?
Sure, sir.
Okay. My screen is visible.
Yes, sir, it's visible, sir.
Okay. Shall I go for full screen or it is okay for this particular screen?
Sir, you go with the full screen, sir.
Okay. Okay.